Today we'll be talking about LoRa. LoRa is a relatively new protocol. It's been around for since I think 2015. It's starting to get a lot of popularity because of IoT. I like it because it's new and so it has some different concepts that we haven't quite seen yet in other wireless protocols. So I think it's worth taking a look at. So the LoRa stands for long range. Its whole point is to be long range. It's always hard to give exact measurements of how far it can go because it depends on the environment. But websites say about 2 miles for urban areas, 6 miles for rural areas. I think that's a little high. I think it's actually a shorter range. But once again, it depends on your environment and how high your gateway is and how what your antenna is like, and so it can really depends on all those things. It's in the 915 megahertz range. So that's something that Zigbee could have been in, but every protocol we've looked at so far has actually been in the 2.4 gigahertz range because these are both ISM bands, so they're free to use without a license. So this will be really the first protocol we've seen that has utilized 915 exclusively. And that's just in North America. In Europe and other countries, it's slightly different frequencies. And this will give you insights into why LoRa is able to go as far as it does because of its lower frequency. If you remember from what we talked about in class, the higher the frequency, the more attenuation it has as it goes through obstacles. So something like 5 gigahertz Wi-Fi doesn't go through walls very well. It can cover roughly a size of a home, medium-sized home, and 2.4 can go a little bit further than that. So the lower you get in the frequency range, the more it's able to penetrate through obstacles. And so 915 megahertz is relatively low, and so it's able to go through a lot more obstacles. So like I said, it's low power. That's a key component to LoRa, is that it's long range and low power. And as a result, it has a low data rate, really low, lower than we've seen for a lot of these protocols, 0.3 kilobits per second to 27 kilobits per second. Depends on what the spread factor you use is the term they use. You can also call it your data rate. So just taking a step back and looking at all the other protocols we've studied, where does LoRa fit into this? My opinion is that it fits right here in terms of it's supposed to be competing with cellular in terms of its distance and even its architectural design. It's a replacement for cellular in some ways, but it's supposed to be lower power than cellular, than traditional cellular. There's newer cellular protocols that are more similar to LoRa in terms of their low power capabilities. But traditional cellular has used a lot of power. And so LoRa is trying to fit into this niche of, well, let's have something that's really can travel really far, can have broad connectivity, but low power. And that's perfect for IoT, as you could guess, Internet of Things devices. You got this remote sensor, that's great. It can be 5 miles away or whatever miles away, and it can just sit there and run for years off of a small battery. So that's the promise of LoRa. If it actually panned out, that's another question. It's so new that hasn't been really used super well, and so we're still trying to actually figure out if it's capable of doing what we hope it is capable of doing. So we're getting more experience as a research community, and there's a lot of interest in LoRa and the different aspects of it. Okay, but this is just a class of wireless protocols that we haven't studied called LPWANs, low power wide area networks. There's other protocols. Sigfox is an example of one. That's, to me, the second most popular protocol besides LoRa. The problem with Sigfox and some of the other protocols is that they're completely proprietary. Sigfox is owned by, I think Sigfox is the company as well, and they own the chip, they own the wireless communication, they own the whole thing. And I'm sure that can have some benefits, but in terms of research and putting it in your sensor, it also has a lot of drawbacks in terms of you have to put all your trust in this one company, Sigfox. LoRa, on the other hand, takes a different approach. It's more open. but it's not completely open, and that's unusual as well. Something like Wi-Fi is completely open, but LoRa actually has a proprietary component to it and an open part to it. And there's some confusion about this. So there's LoRa itself, and LoRa actually just describes a physical layer protocol, which we'll talk about a little bit, and you've watched the video about this as well. So that's the proprietary part. And so in this video you watch on YouTube, this guy reverse engineered it based on the IP, the patents. That's because it's proprietary. Someone owns it, the IP for that. So that's a downside to LoRa, is that there's components of it that are proprietary, the physical layer in particular. But then there's LoRaWAN. It's the LoRa Wide Area Network, and it's all the other layers on top of the physical layer, mainly the MAC protocol and the network, and that's open. But those are two different things. I tend to just say LoRa for all of it. Hopefully when it matters, I will say the right one, whether it's LoRa, LoRaWAN, but people just tend to say LoRa and just mean all those things. But when you get into the nitty-gritty details like we are in this lecture, you want to know that LoRa is a physical protocol and LoRaWAN is things that are built on LoRa. The MAC protocol, the network stack, are all built on LoRa. And this hopefully will make it more clear, this illustration here. So once again, we have our application layer. We're familiar with that. It's where the user code is run. Then we have this LoRa MAC. So that's LoRaWAN because it's got a MAC part of it. There's some options. There's these three different classes, class A, B, and C. We'll talk about that in a second. And then there's the LoRa modulation. So that's what we call just LoRa, the physical layer protocol. And on the bottom of that is the different bands, frequency bands. So like I said, US is 915, Europe is different, Asia and other countries or other regions also have different ones. One thing I do want to say is that you don't have to use the LoRa MAC. There's nothing stopping you from just buying a module, LoRa module, and just using the LoRa physical layer protocol and designing your own MAC. Or maybe you feel like you don't need a MAC because you're only going to use a few devices, and so you can actually just use LoRa itself. And that's interesting because something like Wi-Fi or even Bluetooth, there is no concept of these kind of separate entities. I mean, there is within the spec, but it's not like you can buy hardware that just does one or the other. It comes in one complete package. But with LoRa, there's options to choose one or the other. And it actually depends on the gateway itself more than it depends on the hardware of the end device, whether you use LoRaWAN or not. So let's talk about that, the network structure. So of course, like every wireless protocol, it has its own set of terms. And I'm sure if you use a different term, people would understand. We can use more general terms, but these are the terms that are used by LoRa, and so I think it's good to know that these are what kind of a LoRa person would think of in terms. So you have an end device. So in Wi-Fi, that would be our station. These are the devices that are collecting data or doing something and uploading data to the internet. We have a gateway. And then the topology of this is star of stars topology. And you'll see that in a second. So it's more rigid than something like Zigbee, where it has lots of different configurations or topologies. You could do stars, you could do mesh. LoRa is not like that. It just supports star of stars. And then the gateway is connected through IP to a network server. So this is another case or difference than other wireless protocols, is that the LoRaWAN part of LoRa actually has a lot of different components to it. Something like Wi-Fi, the MAC part of Wi-Fi only has two components, the access point and the station. But with LoRa, and LoRaWAN, I should say, has lots of different components to it. It has the end nodes, which I just described already. These are the sensors. Here's some examples to our left, pet tracking, smoke alarm, water meter, whatever you want. Those are the end devices. And then we have our gateways. So that's what the end node talks to the gateway through LoRa, the physical layer protocol. And then that data gets sent up to a network server. So this is now where we start deviating from other wireless protocols, because now there's this idea of this network server that aggregates all of these gateways together. And then there's the application server. So this is where the application backend is run. And so one thing interesting to point out, it's not a huge deal, but is that it supports 3G, Ethernet, Wi-Fi backhaul. It doesn't say Wi-Fi here, but you could do Wi-Fi as well from the gateway to the network server. So that opens up a lot of potential placements of these gateways. And this is where the star of star comes in. Is that end nodes are connected to the gateway, so that's a star, but then these gateways are connected to a network server. And so that's another star, so it's a star of stars. So you might be asking, or I hope you're asking or thinking, why do we need this network server? Why does Wi-Fi not have it, but LoRa does? And it has to do with the association that these end nodes have with gateways, or the lack thereof. So communication is that end devices are not associated with gateways at all, any specific gateway. That's actually kind of a powerful idea in that if I'm roaming around, it doesn't matter if I roam around, if I move from one gateway to another. The network server is what takes care of that. All the gateways do actually is they're very simple components, is they take LoRa physical layer modulation, convert it into bytes, and then send those bytes to the network server to make sense of them and do whatever they need to with it. So as a result, a transmission, if you have an end node that is between two gateways and it transmits out data, two gateways could receive that data. And so it's the network server's job to take care of the duplicate data. And it's in the payload that it knows that it's duplicate data because it has some kind of sequence number to identify that it's duplicate data. But it's the network server that takes care of that. And so that's kind of interesting, is you could improve the reliability of your system or the redundancy of your system by placing more gateways. And if one gateway goes down, it's okay because maybe that message was being received by two gateways normally, and then one goes down and you still are received by another one. So the network server is what takes care of that duplicate data. Part of the communication, just to be clear about the different components here, the uplink, so this is all from the perspective of the end node, end device. Uplink means that the end device is sending data to the gateway. And downlink is the opposite, that the gateway is sending to the end device. Now it's important to know that LoRa is optimized for the uplink case. It's optimized for sensors or whatever devices uploading data periodically. It's not very optimized for downlink, where the gateway is sending data to the end device. And a lot of these properties that we'll be talking about in terms of its low power capabilities or its scalability, which I haven't talked about, but LoRa is supposed to scale really well to millions of devices in theory. But a lot of these things go out the window if you end up using a lot of downlink traffic. So this is a protocol you would not use a symmetric connection where you want to send some data and receive essentially the equal amount of data back. It's really meant for data being generated on the edge and uploading it to the gateway. Otherwise, a lot of these properties fail. So let's get to these classes. These are important to know, the different classes. We saw this a little bit with Zigbee, that it had two different types of devices. We haven't seen this at all with Wi-Fi. Wi-Fi, is up to you as the application developer to know when you want to send data out into the network. And you could design your application to follow a certain class or pattern of usage. Say, okay, well, I want to be really careful with my battery life, so I'm going to package up all my data and only send it out periodically. What LoRa is doing is they're just defining it more specifically into these three different classes. So in terms of how you want to use your radio and how you're allowed to use your radio. Okay, so Class A, this is the default class. If you are a LoRa device, you have to support this device. And how it works is that end device can send data anytime it wants. So similar to Wi-Fi, it can send its data anytime it wants. But what's interesting about this is that when it sends its data, it then listens to receive a message back. It actually has two receive windows. So there are two chunks of time where it'll listen for a message from the gateway. But other than that, it's never listening to the gateway. So that means it'll only listen to the gateway when it transmits data. So as I put in the slides, downlink communication is only initiated by the end device. So this is the lowest power as you could expect. If a Class A device never transmits, then it'll never receive a message from the gateway. As soon as it does transmit some kind of sensor reading or alert, then the gateway has two opportunities, and actually it can only use one of those windows, but has two chances to send data to the device. And so it uses LoRa. Remember we talked about LoRa, it's a very simple MAC protocol where essentially you just transmit and you hope you don't collide with anyone else. Not very efficient, but it's also very simple. And LoRa is banking on the fact that a device will not be transmitting very often. So once again, the properties of LoRa do not work if you have a device that's transmitting every second or every millisecond or something like that. It only works when you have devices that are transmitting once an hour or once every 5 minutes, or really long time between these readings, or when a door opens. Otherwise, if you have a device that's transmitting much more often, then all the low power capabilities go out the window, the scalability goes out the window as well. So Class A is very simple in terms of the end device is what initiates the connection or sends data and then looks for data. So here's an illustration of that in terms of it transmits data. That's the first section here. And then there's some delay, and then it has to listen. So they call it receive window. It has to listen, say, is anyone going to send me any data? Listen once, and then listen again here. And there are certain rules about if it receives something in the first window, whether it has to listen in the second window. That's specific to LoRa, but I just want you to know that with Class A, it'll only listen to the gateway when it's transmitted data. So I want you to think about this. What are the benefits of this? What are the drawbacks? And I've highlighted some of these already, but let me highlight them again. A benefit would be that you have really long battery life. You don't have to be listening. You don't have to really be using any energy for the radio unless you want to transmit data. So that's really nice. You don't have to be listening into the chatter of the network or anything like that. A drawback would be that there's no way for the gateway to send you data. So let's say I'm a door sensor and I upload data every time a door gets open. But if that door never gets touched, then the gateway has no way of sending information to the sensor. Maybe it wants to change some configuration. Maybe it wants to do an over-the-air update. Maybe it wants to, who knows what it wants to do something. It cannot communicate with that device until someone's opened up that door. So for certain applications, certain instances, that works fine, and that's no problem. Other applications and instances, that's not going to work well. Class A works probably best when you're working with a device that's going to upload periodically. So example is the air quality sensor I've built. We're working on a LoRa version of it. We're planning on using Class A because it's going to upload it'll be a parameter, but we're thinking every 10 minutes. And so we know at least every 10 minutes, the gateway is going to have opportunity to send data to the sensor. We don't expect to send data often, but now it has the opportunity to do that. Another benefit of Class A, I have here in my notes, is that there's no synchronization. So that's kind of nice. It just transmits when it wants to and waits to receive messages. Okay, now let's talk about Class B. Class B is an addition onto Class A. It's not a change from Class A. It's just Class A plus a little bit more. And it's trying to solve the problem of the gateway cannot send data to the end device in a predictable amount of time. So it could be forever before it can get data there. It could be hours or days. So to solve this problem, they want to come up with a way to how do we know when a device will receive a message from the gateway. So how this works is a gateway sends out a beacon on a regular interval. And this beacon purely is to synchronize these devices. So me as a Class A or Class B device would receive this beacon and say, okay, I know that, and then we can synchronize our clock as a result, because these beacons are sent out in a specific interval, and so I can adjust my clock accordingly to match that interval. And what an end device does that is Class B is it opens what they call a ping reception slot every X amount of seconds. It's up to you as a device to choose what you want your X to be. It can be fairly large if you want it to, but you have to have an opportunity to listen at a periodic interval. So let me show you a diagram that might help. So here we have this gateway sending a beacon, and it's periodic here. And so it's able to synchronize its time. So this is a beacon period. And then, so what this end device has done is opened up a ping slot. It's registered itself with the gateway, said, okay, I'm going to open up a ping slot, and this allows the gateway then to send data to the end device during that time period. Okay, so what are the benefits of this, drawbacks? In terms of benefits, it's not that much more overhead. It is listening more, so it's going to use more energy, but it's not listening that much more, and you get a lot more benefit in terms of now the gateway can send data to it at a fixed latency. But there is overhead in terms of that, another synchronization. So once again, it really just depends on the application, what you're trying to build. But I should say also, like I said, Class B is an addition onto Class A. So even with Class B, if you send some uplink data, you still have to wait or listen for 2 receive windows to get data downlink data from the gateway if it wants to send data. So it's not a replacement of Class A, it's just an addition to Class A where you'll be listening a little bit more often. Okay, Class C is different than Class A and B. It's where the device is listening all the time. So this is similar to Wi-Fi, where it's just listening for any message at any time coming from the gateway. Of course, this is going to use the most power. So for a battery-operated device, this is probably not a good choice, though maybe you can get away with it depending on how big your battery is. Of course, this improves the latency, what we call latency, between the gateway wanting to send data and actually be able to send data, because it's instantaneous. Whereas with Class B, it has to wait for that period to happen, and in Class A, it has to wait until the device sends data before it can send downlink data. So Class C, it could be instantaneous. So here's another way of looking at it. On the x-axis, we have here our latency, the communication latency. So Class C is instantaneous. B is, a fixed amount of latency, and Class A is indefinite amount of latency. You just don't know. Of course, you can program your device to transmit, and then but from a theoretical point of view, you don't know when you're going to get that downlink chance to send downlink data. And then on the y-axis, you have battery life. So A performs the best because it was listening the least, and then C performs the worst because it's listening the most. So it depends on the application, what you need it to do. Okay. Now let's talk about acknowledgements here. In LoRa, they're also called confirmed messages. This is not uncommon to see confirmed messages. Other protocols use confirmed messages instead of acknowledgements. I don't know why. I like acknowledgements, I think because I learned TCP first, and this is what TCP uses, but confirmed is another term for this. This is an optional part of the LoRa WAN, and it utilizes the Class A's receive windows. So I send the data, I've opened up a receive window. This gives the gateway opportunity to send an acknowledgement. And me as a device, if I listen and I don't receive acknowledgement, then I know I need to transmit that data again because no one received it, or I don't know if anyone received it. So my question for you is, why would you want this and why would you not want this? Hopefully why you would want this is fairly obvious, given all the discussion we've had about reliable communication, both at the TCP layer and at even down to the Wi-Fi layer and all in between. We want acknowledgements because it provides reliability. Now, as an end device, I know if you receive my data because you've acknowledged it. So that's a really nice benefit. But why would you not want this? And you might think, oh, battery life, and that could be true, but you're going to be listening anyways as a Class A device. You have to be listening after you transmit. So it's not like you're really using that much more battery life. You're already going to be listening. Where this is important is when it comes to the scalability of the network. So let's talk about gateways for a second, then we'll go back to this question, why you would not want to send acknowledgements. So gateways are a little different than a Wi-Fi access point in that gateways are multi-channel gateways. You can have a single channel gateway, but those aren't very good for LoRa. You tend to have multi-channel. Gateways are either 8 or 16 channel. Whereas with Wi-Fi, an access point is only one channel. I mean, there's 11 channels to choose from, but once it chooses that one channel, it's on it, and it's going to be listening on that channel, and all communication is happening here. You could think of it as a correlator to Wi-Fi is that an access point that's listening to all 11 channels at once and is able to receive data from those 11 channels. Of course, those are overlapping channels, so that doesn't quite work. LoRa, the 8 or 16 channels are not overlapping, and so that works. So what this provides for the gateway is scalability. Now, a gateway can be receiving messages from 8 different devices at the same time, or 16 different devices at the same time, which is great for scalability. But now we talk about downlink. And this is where things start to unravel a little bit. Because if a gateway wants to send data to an end device, then it can't be listening on all the channels. It can't be listening and transmitting at the same time. So it has to stop listening to channels and send on just one of those channels to that end device. So now that really kills your scalability, because maybe you need to be listening to all 8 channels at once. You have so many devices that they're constantly transmitting on your 8 or 16 channels. If you have to stop listening and then transmit it, you are blocking out 8 potential people from transmitting during that time because you're transmitting. So downlink is a problem for LoRa. If you send too much downlink traffic, you kill your scalability. So going back to this question of acknowledgements, why would you not want it? It's because it is bad for scalability. What if you had so many devices and all of them had acknowledgements on that they send data and the gateway has to turn around and send acknowledgement and stop listening for a while? If you have enough people transmitting and it has enough acknowledgements, you could actually interfere with yourself and cause nothing to really work properly because you're constantly acknowledging data and stopping other people from transmitting, so they have to retransmit the data, and it could just really clog up your network quite a bit to do this. So a reason why you would not want acknowledgements is because you want to limit how much downlink traffic you're sending. And an acknowledgement is a downlink traffic. It is small. It's a small bit of data, but it is downlink. So then maybe this leads to another question of, well, how do you achieve reliability without ACKs? And this is an interesting topic, and we talked about this with Zigbee already, so I don't think this will be a surprise, but this is an important thing for LoRa because you still want reliability. Who doesn't want reliability? But you don't want to have ACKs. And so, like I said with Zigbee in the last lecture, an option would be to send redundant data in your payload. So instead of saying one temperature measurement, the current temperature measurement, maybe you send that current temperature measurement and 5 of the past temperature measurements in a sliding window kind of fashion. And so if the gateway doesn't receive that one message, it'll miss it, but then if it receives the next message, it will still have redundant data in there. It'll still actually be able to recover all the data because there's redundant data in there. So that is a way to achieve reliability without using ACKs. Once again, it's not perfect reliability because there's a chance that maybe if you put 5 temperature sensor readings in that packet and the gateway doesn't receive those 5, doesn't receive it for 5 transmissions, you could actually miss some data. So it's not perfect, but it does improve your scalability and it does improve your reliability without using ACKs. So once again, it's cost benefits, and you got to choose what's right for your application. For example, my air quality sensor, I want it to be reliable, but I don't need it to be perfectly reliable. So I could put some amount of redundant data, but I don't want to have ACKs on. Would be a compromise. So let's talk about security. Because of the structure of LoRa, there's actually 2 layers of security. There's the network security, and then there's application security. So you have this key network key, they call it, that is embedded into the end device and communicates with and also embedded with the network server. So they have a key with each other. And so all this data is actually going through the gateway without it being able to decrypt the data. And it's only the network server that can decrypt the data. And then there's also a key between the end nodes and the application servers. So that means the network server, which might be an entity you don't quite trust, would not be able to actually decrypt your data either. So it's a layered key structure in terms of you have multiple layers of keys encrypting the data. And so that allows your application server to recover the data, decrypt it, and then send it wherever it needs to go. So the last topic is the modulation of LoRa. And this is interesting, and we're not going to talk about the physical layer very much, but I want you to know this exists. So FSK, frequency shift keying. Just as a refresher, you have some data here. That's the top red line. Some data. And then you have some carrier frequency. This is the green line right here. And you combine those together, and that becomes your modulated signal. So for a 1, you speed up, you increase the frequency relative to the carrier. And when it's a 0, you slow down the frequency relative to the carrier. So that's frequency shift keying. And here's what it looks like in the spectrogram or the waterfall graph, where you have the x-axis is the frequency and the y-axis is time. And so it tends to usually scroll up with time. And then the color is the intensity of the signal. So you can see here this frequency shift keying, it's jumping between two different frequencies. So the center frequency is the carrier, and you can see a 1 or a 0 jumping around like that. So it's just sending 1s and 0s back and forth. So that's just a review. So let's talk about what LoRa does, because it doesn't use this. It uses what they call chirp spread spectrum. And so the idea here is, instead of staying at one frequency to mean a 1, why don't we sweep across frequencies? And this is called a chirp, this one sweep. So you got the sweep rate, how fast it sweeps across this bandwidth. And so what it looks like is to actually send different signals, you have these different chirps. And this is showing the spreading factor here, which I'll get to in a second. But what this provides for you by having it sweep across these frequencies is it provides more resilience. Now, you're not just on one frequency, and if someone is interfering on that frequency, then the receiver's not going to be able to receive the data. You're spreading yourself out across lots of frequencies. And so if one person's interfering in one section of the frequency, you'll just sweep by that. And some of it will be lost, but overall, most of the signal will be recovered, and you'll be able to receive that signal. It's also more resilient to multipath, because multipath affects specific frequencies, and so by sending on multiple frequencies, by sweeping across this with a chirp, you're able to, if you are affected by multipath on certain frequencies, you're going to be sending on other frequencies, and so other frequencies won't be affected by that multipath. So those are the two main benefits of the chirp spread spectrum. And it's all about, for LoRa, just how do we be able to send the signal a lot farther and have lower signal to noise ratio and still be able to recover the signal. So this is just a way to provide better signal to noise ratio is using this technique. So the spread factor is what determines your data rate. The slower the spread factor, or I guess the higher the number, but the slower it is, the slower the data rate, but the more resilient it is to noise, or the farther it can go, whatever you want it to be. So LoRa has these numbers. 12 is the highest number, so it's the slowest spreading factor, and it goes all the way up to 7. And so you can choose as application developer what you want your spread factor to be. I think there is some rate adaptation to LoRa in terms of it can adapt to what it thinks is what's best for the environment as well. Because of course you want to have it as fast as possible and still be recovered, because you don't want to be wasting tons of air time transmitting that data when you could be transmitting a lot faster. So all the benefits of rate adaptation apply similar to they did with Wi-Fi. So I think an interesting thing about LoRa is the community behind LoRa. So there's this network called the Things Network, and it's really fascinating to me, the Things Network. It's this open source community of LoRa gateways. So the idea here is I could set up a LoRa gateway, hook it up to the Things Network, and then anyone can use my LoRa gateway, as long as they have an account with the Things Network. And so this is really interesting. It's this open source network. It's really cool to me. It's a really big deal in Europe, especially Germany. Not so much in the United States. So it has quite a bit of coverage now. You looked a year ago, and the United States was less covered than this. Let's zoom in on the United States. Of course, on the East Coast, it's more. There's got more population. You look at Utah. There's not much here in Utah. In fact, if you want to, we have one on campus that my lab deployed. Some of you are familiar with this because you're using it for your course project. Hopefully it's been working for you pretty well. But we have a Things Network gateway. So that means if you want to design a LoRa product, or if you wanted to play around with LoRa, you could buy a module, create an account with the Things Network, and then you could just use our gateway for free. And I like that. I think that's an interesting idea, to be able to use someone else's gateway for free. Of course, you don't have to go that way. I could, if I wanted to set up a LoRa network and deploy some sensors, I could set up my own private network. But you start running into issues because this is all shared frequency. If you have too many people with too many gateways, it ruins the scalability again, which I've been talking about a lot, because now you're having multiple people transmitting at the same time. If you have multiple people sending beacons or acknowledgements, it kills your airtime. And so there's enough steam here that I feel like the Things Network is a good thing to be part of for scalability and just for interoperability. So that means you could take a device, build it on our network on BYU campus, and then go to Europe and it would work there, assuming you support both frequencies, or go to California or go to Boston and your device would work just fine. And that's in part because a device is not associated with a specific gateway. It's associated with the network server, and that's what the Things Network's providing essentially, is they're providing a community network server for you, and the community is providing the hardware, the gateway hardware, and deploying that and maintaining that. Just as of interest, it's on the Clyde building, on the roof of the Clyde building. There it is. We have a different antenna that we're going to deploy that will give it actually a lot farther range, I hope. So this is zoomed in a little bit. So this is it's actually the Things Network outdoor gateway. So we bought one from the Things Network. There's all sorts of different companies that make these, though. Cisco makes a really fancy one. There's other companies I haven't heard of before that make them as well, of various sizes and shapes and cost. There's indoor gateways as well. Just for your interest, this antenna is the GPS antenna, and this antenna is the 3G antenna. So if you want to use cellular, which we actually don't use, we just plugged it in to block the water coming in. But if you want to use cellular, you had a SIM card, you could send that, plug that into this device, and then you wouldn't even need Ethernet. You would still need power, but you wouldn't need Ethernet or the internet to connect. You could just use the 3G. We're using what's called power over Ethernet. So this Ethernet cable is providing data and also power to power up this gateway. And so it's been really great. We've had it there for the whole semester, I'm pretty sure. And it's been working surprisingly well. I'd like to, some of the groups actually are going to do some site surveys to see how well the gateway works in terms of range. And then that will inform us if we should put another one on campus. I'd love to put another one on campus or another one in Provo and build out this network. My parting thoughts for you are the Things Network, this interesting idea, this open source community, or not open source, but this kind of open community of gateways. So my question for you is, why not for Wi-Fi? Why doesn't this exist for Wi-Fi? And there's no right answer to this. I don't know ultimately. I have some ideas. I think one is that Wi-Fi's range is not very far, and so there's not much of a kind of community idea here. It just works in your home, and so it's kind of Wi-Fi is more of a private thing than something like LoRa, where it goes miles, 2 to 6 miles, and so it becomes more of a community thing as well. I think there's just the right place at the right time. with IoT becoming a big thing, you don't want, if you're building a sensor, you don't have to worry about the network as well. It'd be really great if the network just was provided for you. And so that's something that the Things Network is offering to you, is that don't worry about the network, just make your thing, your fancy Internet of Thing device, and we'll take care of the network. With Wi-Fi, the hardware tends to be pretty cheap, and so it's easy to deploy infrastructure. And the infrastructure doesn't have to be very big because it just covers a home. So these are different reasons I imagine why this doesn't work for Wi-Fi, or it hasn't really taken off, this idea for Wi-Fi. And then my last question for you is, do you think this will work? Do you think the idea of the Things Network is scalable to the Internet of Things? Do you think this is something that's going to take off? The Things Network is a big deal, but it's not everyone's heard of it. It's not like the end-all be-all of LoRa. Plenty of people also deploy their own private LoRa networks. And so do you think this is something that will eventually just take over all of LoRa and the Things Network will become one and the same with LoRa? Or do you think there's issues here? I mean, one thing I would say is economic incentives of a company. Can they use the Things Network? And do they have incentive to use Things Network or to provide their own infrastructure and their own control so they can have a competitive edge or something like that? So economics might not be there. I'm not sure. I'd have to think about that more. But once again, I like the idea of the Things Network. To me, it's just different and refreshing that we have this open community of gateways that anyone can use and not have to worry about the network itself. Okay, well, that's it for LoRa. Feel free to ask me questions in Slack if you have any. Thanks.